So it's my pleasure to introduce Dr. Pallavi Dani, and she will talk about subgroups of right-angled Coxeter groups via Stallings-like technique.
Okay, thanks very much for the invitation, and thank you all for coming to my talk. And yeah, so I'm sorry I wasn't able to be there in person. Okay, so I'm going to talk about subgroups of right-angled Coxeter groups via Stallings-like techniques. So all of this is joint work with Ivan Levcovitz. And so let me, wait. All right. Yeah, so I'm going to begin by saying what I mean by Stallings-like techniques. So the Stallings introduced this topological way of thinking about questions about subgroups of right-angled Coxeter groups. Oh, sorry, subgroups of free groups. And so this kind of revolutionized how people thought about these things that were previously thought of as combinatorial questions. And then it led to sort of many generalizations. So I'm going to start by just talking about the free group version. Okay, so free groups and their subgroups. So let F be a free non-abelian group of finite rank. So for definiteness, I'm just going to say F is equal to the free group generated by two generators A and B. And so consider some finitely generated subgroup H, which is given by some finite list of elements, W1 up to Wn. And so each Wi here is some word in the generators A and B. Now it's well known that H itself is a free group. And there are lots of other questions that you might be interested in about H. So for example, what is the rank of H? What is the basis for H? Is the index of H in the free group finite? Is it normal? Given a word in the generators of F, does that word represent an element of H? So that's known as the membership problem. Or given another finitely generated subgroup K, can you compute the intersection of these two? So yeah, so there's all sorts of these combinatorial type questions. And it turns out that, so many of these had combinatorial solutions before this approach, but they can be approached by this nice topological method called Stallings folds. So that's what I'm going to talk about next. So Stallings folds and graphs are the following. So let's say you have lambda, a directed labeled graph. So what you should be thinking about is a graph that's kind of like the Cayley graph, or either like a Cayley graph or the quotient of the Cayley graph of the group. So its labels are actually the generators of the free group. And the directions coming from, it's just like the directions on the Cayley graph. So what a fold operation does is if you have a vertex where you have two different edges with the same label coming out of that vertex, then they get identified. So just like in my picture there. And a graph is folded if you cannot perform any such moves. So how do you apply this? So this is a very simple concept. How does it help to study subgroups? Well, okay, so let's stick to the free group, free generated by A and B. And again, we have some subgroup. And now I'm going to pick, just for my example, I'm going to pick a specific subgroup of F given by these generators here. So A B inverse, B A B, A B B. Okay, so here's just for definiteness to illustrate. So what do? You start with a rows graph labeled by the elements of S. So in this case, we have 3 elements. And so you just subdivide these petals and label them with the words that you have as your generators. And then you start performing folds if it's possible. So in this example, I see that over here from this vertex, I have 2 different edges labeled B coming out with the same orientation. And so they can be folded. And so that's what I have in my second picture. And then again, there's some more folds you can perform. So you have 2 A's coming out of that same vertex and 2 B's coming out of that same vertex, again with the same orientation. And so again, you can fold those. And now you observe that this last object here has the property that no more folds are possible. And so this folded graph that we arrive at the end is something that carries a lot of information about the subgroup H. So for example, you can use it to determine the basis or a basis and the rank of H, right? So in this example, I have a subgroup generated by these elements here. And so once again, I start with this rows graph on these 4 petals with the labels. And then I perform a series of folds, just like we did before, and I arrive at this graph at the end. So notice that initially I had 4 loops, but in the process of folding, I managed to collapse this loop at the bottom on the 3rd picture around. So by the way, each of my arrows here is not a single fold, and just sort of for the sake of brevity, I've just performed multiple moves in each of these arrows. But this last object here now is a folded graph, and what it is a graph whose fundamental group is the group H. And so the rank of H can be computed by computing the rank of the fundamental group of this graph, which can be done by just choosing a maximal tree and seeing how many edges are not in the maximal tree. And similarly, you can use the same maximal tree to pick a basis for this free group. So this clearly gives a method for finding the rank and basis for any finitely generated subgroup of the free group. Similarly, you can determine the index using the same thing. So I'm going to introduce some terminology, which is not necessarily standard terminology, but it was what we used in our generalization. So we say that this graph lambda H is full valence if every vertex has an incoming edge and an outgoing edge corresponding to every generator, right? And so in my first example here, you see that this vertex here has valence 3. And so there's no outgoing, or there's no incoming A here. So this does not have full valence. But you can go through and check that in my other 2 examples, they all do have full valence. And so it turns out that, so if the subgroup has finite index, if and only if this lambda H has full valence. And moreover, the index of H is just the number of vertices in lambda H. And this is just coming from covering spaces. So if this graph has full valence, then lambda H is actually a covering space of the rows graph with labels A and B. And so the index then can be computed because it's a covering space. Okay, so similarly, the other problems that I mentioned in the beginning can also be treated using this object lambda H. So there's sort of ways of thinking about what all these things are in terms of topological properties of this graph lambda H. And so this was sort of a very influential idea, and it's been used a lot in the study of free groups and even outer automorphisms of free groups, but also there have been generalizations to other settings. So this technique has been adapted even in the case where the groups are not free. This case is a little bit trickier because the other groups have relations, and so you have to kind of deal with the relations. I mean, and then in the case of the free groups, the terminal object was something whose fundamental group was the graph that you get at the end. And so, and that's what helps with all these characterizations. And so you have to, so when you have relations, you have to work a little harder to sort of get those same properties. Nevertheless, this has been carried out in all these, they had already been carried out in all these different settings. So, the first people, I think, to do it in a non-free setting were Arjantseva and Olshansky, who sort of proved something about generic groups using some folding type ideas. And then Shoup adapted it to extra large type Coxeter groups. McCann and Wise did something for small cancellation groups. Kharlampovich, Miaznikov, and Bay considered a lot of algorithmic questions using Stallings-like folds for automatic groups. And then more recently, sort of in a different direction, Baker and Lazarovich thought about certain groups acting on cat zero cube complexes. Now, one thing about all these, everyone sort of just kind of did these things ad hoc for their particular setting. So they're all a little bit different and have different features. And another thing I should say is that this class of automatic groups that I mentioned here is actually pretty large and does actually cover right-angled Coxeter groups. And so some of the things that questions that one might want to answer for right-angled Coxeter groups could already have been done using the Karl-Lampovich, Myasnikov, phase stuff. But because that automatic group is very general, that sort of restricts, how much you can actually do with the object that you get there. So what our goal was to develop a generalization which was well suited to right-angled Coxeter groups. So we're going to be able to generalize a lot of the same things that were true for free groups. And okay, so one big distinction was that automatic groups are not necessarily cat zero, whereas right-angled Coxeter groups are. And so we were able to use a lot of cat zero type stuff to actually be able to go further. Okay, so just to kind of remind everyone, right-angled Coxeter, I think everyone probably knows what a Coxeter group is, and the right-angled ones are just ones where the exponents are either 2 or infinity. And now the unfortunate thing is that, contrary to what people might be used to, we define them slightly differently in terms of the defining graph rather than the Dynkin diagram. And so if gamma is the defining graph of a right-angled Coxeter group, then the generators are the vertices of the graph, but you have an edge whenever the two generators commute rather than if they don't commute. So it's kind of the complement of the Dynkin diagram. Okay, so that's what so here are just some examples. So if you just have two vertices with no edge, then it's a free product of two Z2s. And on the other hand, if you have an edge, then it's a direct product. And here you have a situation where you've got D infinity, or in other words, Z2 star Z2. But if you have a square, then you've got two D infinities which commute, and so you get D infinity cross D infinity. Okay, so those are just some basic examples of going back and forth from the graph to the group. Okay, so that's what a right-angled Coxeter. That's how I think about right-angled Coxeter groups, and it's kind of natural to think about them this way when you're thinking about geometric group theory. Okay, so right-angled Coxeter groups act on certain very nice cube complexes. So they act properly and co-compactly on certain simply connected cube complexes. And the generators act by reflections and hyperplanes that intersect at right angles. So that's sort of where the right angle terminology comes from. A cube complex is simply a CW complex in which each cell is isometric to the Euclidean cube of some dimension, and the attaching maps are restrictions of Euclidean isometry. So something like this. So you're allowed to have loops and cylinders and things like that, but each cell is a cube. Okay, so what are the objects that are going to generalize graphs? Because we have these extra relations, we need something more than just the graph. But because all the relations are commuting relations, it's going to be enough to just look at cube complexes. So what we want to consider is cube complexes, which are what we call gamma labeled. So you should think of these labels again as generators of some right-angled Coxeter group. So each edge of the complex is labeled by some vertex of gamma. And because all the generators are of order 2, it's more convenient to just assume that to just take the edges to be unoriented. Okay, and then opposite edges in squares have the same label. So this is what you would expect, say in the Cayley graph of, or the presentation complex of one of these right-angled Coxeter group. And so we want to only consider complexes which have this property. And finally, if you have edges that are all incident to the same vertex in the cube complex, and those labels all form a clique in the graph gamma, then there should be an actual cube there in the cube complex that fills in that sort of tells you that those generators mutually commute. So, so these are the three properties that the natural cube complexes associated to right angle Coxeter groups have. And so we want to consider complexes with this property. Okay, so that's how we generalize the graphs. Now, what happens with the folds? So in the free group setting, we had foldings of graphs. So we have that here too, because we do have underlying our one skeleton are graphs. And so foldings, so again, if you have two edges with the same label, this time you don't have orientations, but you just collapse the edges. Now there's sort of a subtlety that I kind of glossed over a little bit when I was talking about free groups. The picture could be more complicated than just that one type of fold, right? So it could be, you know, just they could have two vertices in common, in which case you just collapse. But in these last two pictures, you could have a loop and an edge or two loops, and then you just collapse it to a loop. And as you can see, because of the lack of orientation, there's some ambiguity here about how you would collapse it. So you just have to pick one. So there's some choices involved, which we didn't have earlier. So that is going to build in some non-uniqueness to the final product that we're going to get. But it turns out not to matter. It still sort of carries the information that we want it to carry, even though it's not unique. Okay, and then of course because we have cube complexes instead of graphs, we have the higher dimensional analog of folds. So we've got cube identification. So let's say you have a bunch of different cubes with the same boundary, then you would want to just collapse them to a single cube with that boundary. So it's just similar to that second picture we had. Similar to the second picture that we had in this slide. You have two different edges with the same boundary, you collapse them to a single edge with the same boundary. Okay, now finally, because we have these relations, we have a third operation which doesn't have any analog in the first two, in the free group setting, which is that if you have a place where there should be a cube, you should attach a cube. Okay, so we call this a cube attachment operation. So if you have a vertex with some edges emanating from it, and the labels of those edges form a clique in your graph, then that tells you that those elements should actually commute in the right angle Coxeter group. So there should be a cube there, which tells you that. And so you attach a cube. Usually you would only attach a cube if there isn't already a cube there. Okay. So those are our three operations. And now we need to know how to stop, right? So in the free group setting, we stopped when we arrived at a folded graph. And so here we have the notion of a folded complex where you have no fold or cube identification operations possible. So no more, there's no possibility of either identifying edges or identifying cubes of higher dimension with the same label. But that's not enough, because we also have this third operation in this setting, which is attaching a cube of any dimension, right? And so how do you know when to stop attaching cubes? Well, this is what I meant in the previous slide when I was saying you only attach a cube if there isn't already one there. So if we say that a complex is cube full, if everywhere where there should be a cube, there already is a cube. So in other words, I'll just do it by example. So in my picture on the left, I've got a central vertex with edges labeled A, B, and C coming out. And in my graph defined on top here, I noticed that A and B have an edge, which means they commute. So there should be a square representing that relation. So on the left, I don't have a square there. So that is not cubeful. But on the right, I do have a square. So it is cubeful. And okay, so these are the two properties that we're going to be looking for to know when to stop our folding procedure, our sequence of moves. Okay, so now we get to, actually defining this terminal object, right? So we start with a gamma labeled complex, and then we start performing a sequence of these moves, which we've just defined. So a fold or a cube identification or a cube attachment. And so now there's immediately a problem, because in the free group setting, all we had was folding, and then eventually, because folding always reduces the number of edges, eventually this would stop. But in this case, we also have this thing where we attach cubes. And so you could just keep attaching and folding and attaching and folding, and this process might never stop. Nevertheless, you can still take the direct limit of any such sequence. And so you can define this object called omega x. But it's not always going to be it's not always going to carry the information that you want, right? Because you could sort of choose a very silly sequence of moves where we just sort of focus on one spot in the complex and keep attaching and folding and attaching and folding while completely ignoring a different direction. So you don't want to look at all such, or you don't want to look at any such omega x. So what you want to look for is an omega x which has these two nice properties that we just talked about. You want to look for an omega x which is folded and cube full, and in that case, it's going to carry the information that we want. So such an omega x is what we call a completion of x. And this terminology of completion is sort of motivated by the paper of Levcovitz, Levcovitz on automatic groups. So they sort of define a similar sequence. They're not doing cubes, and they actually don't have two cells, but still there's some similarities between what they do and what we do. And so we call that completion inspired by their terminology. Okay, so like I said, you might think, well, how do we know this even exists? Well, it turns out it's not too hard to show that if you start with a finite complex, then a completion always actually exists. So there's always going to be some way of doing these moves in such a way that you end up with a direct limit, which is folded and cube full. Now, it might not be finite still, but that's okay. Okay, and now we want to talk about how this relates to subgroups of a right angle Coxeter group. So if you look at a subgroup given by some finite generating set, then again, just like in the free group setting, you can start with a rows graph with the labels of the rows graph being the generators of the group. And then you can start performing these moves and get a completion of this XS. And a completion of the group is just a completion of this object XS. So let's do an example. So here is an example where I have a graph gamma consisting of one triangle and two vertices. And so I'm going to pick a definite subgroup, ADB and AEC. And this is my generating set S. And so then XS is just a rows graph with those labels. And then I can start performing moves. So I see that out of B, there are two A edges coming out. And so the first thing I can do is fold the two A's to a single A edge. And then I see that in my graph, A, B, and C commute. And so I can attach a cube to reflect that. And so I now have this object, and now I can see that there are no more folds and no more cube attachments possible. And so what I have is a folded and cube full complex, and so that's a completion. So this is one where the completion did actually end up being finite. Let's see another example. Here my example is the graph gamma, which is a square. So 4 generators. And my subgroup is just a single generator, ABCD. And so this loop, the rows graph associated with that is just a single square. And again, I can start performing these moves. Now you can see right away that there are no folds possible. But what you can do is attach a cube because, for example, in my graph, red and green commute. And I have a red edge next to a green edge. And so I can attach a square along those two edges. So that would look like this. But then I see that blue and purple also commute. So I can attach a square there. And I can basically keep going, right? Next, I can attach a square corresponding to green and blue as well as red and purple. And you can see right away that this process is never going to end, right? Both inside the square and outside the square, you're going to be able to just always add more and more squares. And so the end result is going to be sort of a bi-infinite cylinder that's tiled by squares. And okay, so this is an example where this completion ends up being infinite, but this bi-infinite cylinder, you can actually check that it is folded and cube folded. Okay, so those are two sort of different examples. Okay, so now I want to talk about a new issue, namely quasi-convexity. This is an issue that doesn't come up in the context of free groups, but is intimately related to these completions. Okay, so let me remind you of what the Cayley graph is. So the Cayley graph of a group is just a graph whose vertices are the elements of the group and the edges are, you have an edge between two vertices if they differ by a generator, right? And so this gives you a metric on the group. So when you talk about the word metric, that's what people mean. It's a metric on this Cayley graph. And you say that a group is quasi-convex if there's some constant, a uniform constant, so that anytime you take a geodesic in the ambient space whose endpoints are in G, that geodesic must lie in the M neighborhood of, is there a question?
Yeah, there's a question. So now, Joseph asks, how do you use this completion to compute invariant of the subgroup?
To compute
the invariant of subgroup.
In the free group case, you computed the round of the X.
Sorry, I didn't hear that.
So how do you use this completion to compute invariance of the subgroup? So that's the question.
So I'm going, right. So I mean, what you can use it to compute some things, which I'm going to get to. So you can use it to compute the index of the subgroup and some other things. But the first issue I want to talk about is how the completion relates to this notion of quasi-convexity. Yeah, anyway, so I'm not sure that answers the question. So is that the question in the chat? Yeah, so I mean, it's, yeah, maybe let me just go on with my talk and we'll see if that answers the question. So quasi-convexity is a property of the subgroup, and we'll see in a minute that the completion detects quasi-convexity. And then later on, I'll get to how to determine whether the group is finite index, which I'll also spend some time on. Okay, but I wanted to start with this notion of quasi-convexity because it's sort of a really nice application of completions. And so, right, so quasi-convexity, so I mean, it's just a quasification of the notion of convexity, right? So when you have, geometry, where you say that something is a set is convex if, the geodesic between any 2 points is lies within the set. So a quasi-convex means the geodesic between 2 points is close to the set. So there's some uniform constant such that any geodesic between a pair of points has to be within that uniformly bounded neighborhood of the set. So that's what it means to be quasi-convex. And as you can imagine, quasi-convexity is a very useful property in geometric group theory. And so it's nice to know whether a particular subgroup that you are interested in is quasi-convex or is not quasi-convex. And in the free group, this doesn't arise because all finitely generated subgroups of the free group are necessarily quasi-convex. So that's why I didn't mention this before when I was talking about free groups. But here's a really nice thing is that quasi-convexity exactly corresponds to every completion for G being finite. So remember, So remember, we had our two examples. In our first example, we computed the completion, which was this finite object here. And so that group, that tells me that that group is quasi-convex. On the other hand, in our second example, we had this subgroup. So we had gamma given by this graph, and then the subgroup generated by ABCD, and we saw that the completion was infinite, and that tells me that that subgroup is not quasi-convex. Now, for this particular subgroup, it's not hard to see directly, probably combinatorially, that this is not quasi-convex, but it's just supposed to illustrate that, you know, that these completions are detecting quasi-convexity. And so, you know, as we saw in the free group case, you always end up with a finite graph, and so, and that corresponds to the fact that every finitely generated subgroup is quasi-convex. Okay, so I mean, now we have some applications of this fact, namely, you know, we can show that certain subgroups, natural subgroups of right-angled Coxeter groups are actually always going to be quasi-convex. So one of the classes that we tackled was, if you take any subgroup that's generated by finitely many reflections, then that subgroup is quasi-convex. And as an application of that, we show that in certain settings, so when gamma is triangle free, which corresponds to the cube complex associated with it being two-dimensional, in that setting, we can show that every one-ended subgroup, which is isomorphic to some Coxeter group, is quasi-convex. So the idea is that you can, you know, using just the fact that it's finitely many reflections or the fact that it's isomorphic to a Coxeter group, you can show that you can basically construct a finite completion, which shows that it's quasi-convex. And so you can sort of do this for, you know, use this to show your favorite class of or examples of subgroups are or are not quasi-convex. But one of the sort of even more exciting applications to me is something we did more recently, which is that we use this notion of completions to provide a new method of constructing one-ended hyperbolic subgroups with non-quasi-convex subgroups. So I think, I know Ignat Sorokin mentioned hyperbolic groups in his talk, so that's sort of a very big topic in geometric group theory. And so a lot of subgroups of hyperbolic groups turn out to be quasi-convex, and it's actually kind of hard to come up with non-quasi-convex ones. And there are many examples out there of such non-quasi-convex subgroups of hyperbolic groups, but they're all basically coming from two types of constructions. One is they're kernels of certain homomorphisms, and the other is their H and N extensions constructed in such a way that the subgroup, the vertex group in the H and N extension is distorted. So there's sort of two methods that have been used for a long time to construct such subgroups. And so this method of using completions to detect non-quasi-convexity gives sort of a totally brand new way of constructing non-quasi-convex subgroups of hyperbolic groups. So what we actually do is we give a construction where we have as input some subgroup of a right-angled Coxeter group where the subgroup is non-quasi-convex. So here the right angle, in the input, the right-angled Coxeter group is not necessarily hyperbolic. And such examples are plentiful. Basically, anytime you have a product, a non-trivial direct product, you can come up with non-quasi-convex subgroups. And what the construction does is it spits out a graph gamma prime and a subgroup H prime of W gamma prime, so that the subgroup is still non-quasi-convex, and the new group is actually, the new right-angled Coxeter group is actually hyperbolic, one-ended hyperbolic. And so this construction also has a lot of flexibility, so you can use it to sort of give examples with, you know, prescribed properties, so that, you know, can give an example where H prime is not finitely presentable, or it is finitely presented, or, you know, it has various properties that you might care about, could be preserved by this construction. And so it's got a lot of potential for new examples that people might want for various applications. Okay, so right, so that's sort of the applications of quasi-convexity. And just to remind you, so I wanted to talk about quasi-convexity first because it's characterized by this very basic property about completions, right? Namely finiteness. Completion finite is equivalent to quasi-convex. So the next thing that you might want to consider is the index of a subgroup. And so every finite, so if you, so in the free group case, we were able to detect whether or not a subgroup is a finite index. And so you might want to do the same thing here. And if a subgroup is a finite index, then it is necessarily quasi-convex. And so definitely one of the things that you're going to require when you want the subgroup to be a finite index is the completion should be finite because it has to be quasi-convex. And the other property is the same property that we had in the free group setting. Namely, that if you have a gamma, so define a gamma label complex to be full valence if for each vertex and each label, there's an edge incident to that vertex with that label. Okay, so just like what you would have in a covering space, basically. And it turns out that that's enough. So you given a subgroup of a right angle Coxeter group with a finite generating set, the completion detects the index and determines if it's finite index. And so in particular, G is a finite index if and only if the completion is finite and it has full valence. And then the valence is just equal to, the index is just equal to the number of vertices, just like we had before. I should say in this case, it's not always true that the completion has fundamental group equal to isomorphic to the group, but it is true when the group is torsion free. But if the subgroup is not torsion free, has torsion, then yeah, then it's not even equal to the orbifold fundamental group or something. Okay, so but yeah, anyway, so this still does detect index, and so this was actually the original motivation that sort of led us down this path, because we were actually thinking about a question about commensurability. Oh, actually, let me do this example before I talk about that. So yeah, so just quick example. This was the example that I already did, and the end result here is a complex, which is clearly not full valence. It is finite, so the group is quasi-convex, but it's not full valence because you can see that there are vertices which don't have pink and purple edges coming out of it. And so that's not a finite index. Whereas here's a new example. So that's my graph. And here's a subgroup associated to it, generated by AC and BC. So anyway, so you start with this, you do this procedure of folds and attaching cubes, and you end up with something like this. And in this case, the end result has two vertices, and they all have all three generators coming out. And so it does have full valence, so it is a finite index. Okay, so those are sort of the two examples of things that could happen. So as you can see, it's very easy to detect the index. Right, so going back to what I was saying, this was sort of our original motivation for coming up with this notion of foldings in the first place, which has to do with commensurability. So this is sort of an application, which is sort of a sidetrack here. There's a well-known result of Davis and Januszkiewicz, which says that every right-angled Artin group is commensurable to some right-angled Coxeter group. And the converse of this is very far from being true. So it's easy to see that using quasi-isometry and variance, for example. So you can, I forgot to put the definition of commensurability, but what I'm talking about here is abstract commensurability. So I say that two groups are commensurable if they have subgroups of finite index which are isomorphic to each other. Okay, and so so if you have that two groups are commensurable, then that implies that they're actually quasi-isometric. I'm not going to define quasi-isometry, because it's not really super important for the rest of my talk. But anyway, so commensurability implies quasi-isometry. And it's very easy to, and there are lots of quasi-isometry invariants. And so you can find, it's very easy to show that there exist right-angled Coxeter groups, which are not quasi-isometric to right-angled Artin groups, and therefore not commensurable to any right-angled Artin group. On the flip side, so this question was lying around for quite some time, which right-angled Coxeter groups are actually commensurable to rags? And it's also not even known which right-angled Coxeter groups are quasi-isometric to rags. But it is known in a particular setting, namely Nguyen and Tran characterize right-angled Coxeter groups, which are quasi-isometric to rags, in a particular setting, which is one-ended, planar, triangle-free defining graphs. And so in that setting, they can say exactly, if you start with a right-angled Coxeter group within that class, they can say exactly which ones are quasi-isometric to rags and which ones are not. And so the ones that are quasi-isometric are the candidates for being commensurable. So it's a question like, are these just all commensurable or are they not necessarily commensurable? And it turns out that, so what we proved was that in fact, in this context, being quasi-isometric and being commensurable are equivalent. So in fact, all three of these things are equivalent. W gamma is quasi-isometric to a rag, is commensurable to a rag, or contains an index 4 subgroup that's actually isomorphic to a rag. So clearly going up is easy. If you contain an index 4 subgroup isomorphic to a rag, then definitely you're commensurable to a rag, then definitely you're quasi-isometric to a rag. So the hard direction is 1 implies 3. And so the idea there was to start with, because we're in the context that Nguyen Tran already characterized which ones are quasi-isometric to a rag, we just start with their description and take those groups, and then we explicitly construct some subgroups. And the application of completions is to then use completions to show that those explicitly constructed subgroups actually have index 4. And then we use different methods to show that they're actually isomorphic to rags. But the completions form a really important part of that argument. Okay, so that's sort of an application of completions and detecting finite index. There are lots of other algorithmic applications that we can do. So, for example, so I should say that let's say you already somehow know that a particular subgroup that you have is quasi-convex. Then that tells you that the corresponding completion is finite by what we proved. And so once you have a finite completion, then any other property that you can characterize can be algorithmically detected because you have this finite completion. So you just have to check finitely many things. And so using this idea and characterizations of these properties, we can determine algorithmically whether or not a subgroup is torsion-free or whether it's normal, or given any G, determine whether some positive power of G is in the subgroup G. And a lot of the other problems that I mentioned in the context of free groups can also be done using completions. I'm not mentioning them here because you could also have solved those algorithmically using the automatics group stuff. So you could do it using these completions, but that was already known. And let me mention one last algorithmic application, which is we also give an algorithm, this time not just for quasi-convex things. This is just start with 2 right-angled Coxeter groups, abstract. One is triangle-free and one-ended, and the other one is just any gamma prime. Then we give an algorithm to determine whether or not W gamma prime is isomorphic to a finite index subgroup of W gamma. And again, this uses completions. Subsequently, Genevois gave an algorithm to determine this without the finite index without the finite index properties using completely different techniques. Okay, so yeah, so let me stop there.
Yeah, I think question in the chat. So, yeah. So,
Oh, is there a question? Okay.
May I ask a question?
Yeah.
So first you had this like that you were putting the edges together for the three groups, right?
Yeah.
And then you started adding these cubes.
Yeah.
So is this, I mean, maybe you were saying the motivation, but like, do you also have this for the free group, or this is like a special thing for the Coxeter group, or?
Right. So for the free groups, you don't have to. So the goal is to kind of, I mean, one of the things that ends up being really important in the, terminal object is a property that gets used a lot is that this terminal object should have the property that any reduced word which represents an element of the subgroup should be the label of some path in this terminal object. So in the free group, you don't end up having to attach anything because you already get that property without doing that. But because the free group doesn't have any relations. But in the setting of more, any group that's not free, you have some relations. And in order to get this property that every representative of a group element should be, every reduced representative of a group element should be some path in the completion. And so the only way you're going to be able to get that is by actually attaching these cells corresponding to the relations. The fact that they're cubes comes from the fact that these are right-angled Coxeter groups. If you had if you had other groups, then you would just have some relations. And a lot of people, when they generalize it to other groups, they didn't necessarily actually add physical two cells. They just kind of thought of it as a graph, but secretly they are attaching a two cell because they're attaching the rest of a relation. So that's why you have to kind of add these relations, is because you want this property, you want the final thing to have this property and to be as close to the fundamental group, to something which has the group as the fundamental group as you can.
Thank you.
is there any other? Yeah, if not, let's thank to the recording.
Thank you.